In the last video, we discussed about the exponential growth model and logistic growth model, right? Where dy over dt equals to ry, where y is the population and r is here the growth rate, which is positive, and initial value of the population is y sub 0. This is the exponential growth model. And the other one was dy over dt equals to ry times 1 minus y over k, where y at 0 is y0 and r positive is called the logistic growth model. This r is also called the intrinsic growth, okay? Intrinsic growth rate. So what is happening, why it is different from that is this exponential growth model implies that the population increase infinitely. It keeps increasing, okay, for r positive. And this the logistic growth model says that if the population is above the carrying capacity, then this will become the y over k. If y is bigger than k, carrying capacity, then y over k is greater than 1, and 1 minus greater than 1. This factor will be negative. As a result, the dy over dt will be negative. In that case, if you start from a population that is bigger than its carrying capacity, then this population starts to decline. It will grow down, it will decrease. And if y is smaller than k, then this factor will be positive. As a result, you will get the rate of change of the population will be positive, okay? In that case, it will grow, okay? So the next thing is we want to consider similar to the logistic growth, but a little bit different by the sign. We call critical threshold, because not all population grow if they start from like very small number, okay? So population needs to be a certain number to grow, okay? We call that threshold number, okay? Look at this, dy over dt equals to ry, where r is positive, ry, y over t minus 1. If y is smaller than t, what happens? This will be less than 1, right? Less than 1 minus 1. So this quantity will be negative. And then as a result, dy over dt will become negative, meaning that if the population starts from really small number, in that case, the population may not grow, okay? It may decline instead. But if the population start from a number that is bigger than certain threshold, in that case the population, this factor will be, because for example, if y is the population, y is bigger than t, then this will be bigger than 1, right? And bigger than 1 minus 1 will be, this factor will be positive, meaning that dy over dt will be positive. So this t is called the threshold value, okay? So here t is a threshold value. Now we want to basically analyze this model. So how do we analyze this model is, let us first find out the equilibrium point. So let me use different color for that. So equilibrium point. So how do we find out the equilibrium point or equilibrium solution is, you said the derivative 0, right? Dy over dt equals to 0, right? So how do you do that is, if you do that, then ry times y over t minus 1 is equals to 0. So either ry equals to 0 or y over t minus 1 equals to 0. This implies y equals to 0 is one solution, and this implies y equals to t is another solution. So we usually denote the equilibrium solution as y, so 0 y star, then or star of any variable 0 and t. So these are the equilibrium solution, okay? So if you want to know the stability, actually we want to know the stability of that. So how do I find out how do I determine the stability of this? So what you need to do is you need to plot y versus f of y, right? So y versus f of y. So how would that look like? You see that. So what is the right hand side? The right hand side f of y, right? So this one is f of y. So f of y is ry. So here f of y, you can write f of y equals to ry minus so ry square over t, right? Ry square over t minus ry. This is what you get, right? So this is a quadratic. R is positive, t is positive. So this is a quadratic with the leading term positive, meaning it will have a parabola that is concave upward, right? But where does it intersect the y-axis? This horizontal axis is when we set that equals to 0, f of y equals to 0, then you will get that we got 0 and t, right? So you got 0 and t, and we have a concave up parabola. You see that? This is what you get, 0 and t and concave up parabola. So if you want to know what is that the vertex, to find out the vertex, you do h equals to negative b over twice a. That will be negative r over 2 times r over t, right? You get t over 2. And similarly, if you plug in t over 2 here, what do you get? So k, because we did not buy hk, right? The vertex is, it is from the college algebra, is f of f at h. So that will be r over t times t squared over 4 minus r times r over t, right? What do you get? So you get, y is t over 2, not r over t. T over 2, right? So you get r times t over 2. So what do you get? If you simplify this, you get t and t cancel out. So rt over 4 minus rt over 2, right? That will be negative rt over 4. So that will be t over 2 and then negative rt over 4. That is the y value, right? Let me write this a little longer. Okay, that will be negative rt over 4. Okay, so this is what we get. Now look at this. So whenever the value of y is less than 0, in that case, what do you see? If the value of y is less than 0, then f of y is positive. Means f of y positive means dy over dt is, that is f of y, right? dy over dt is positive, that is increasing. And between 0 and t, between 0 and t, f of y is less than 0, right? Because it is below y, that axis. Less than 0 means dy over dt is less than 0. So it is decreasing. Y is decreasing. Similarly, this one will be, y will be increasing. So what do you see? This is stable, right? And this is unstable. You see that? So this is stable and this is unstable. Now, so there is another way to check the stability, right? So alternative way to do that is using the linearized form. That is, what is f of y? F of y is ry square over t minus ry, right? So to check the stability of this linearized form, you need to find out f prime of y. That will be 2ry over t minus r, right? So at y equals to 0, you get f prime at 0 equals to negative r, which is negative. So it's stable, right? This y equals 0 is stable. At y equals to t, what do you get? F prime at t equals to 2r minus r, right? Because you replace y by t and t will cancel out. So which is positive, so unstable. We saw that already from the phase diagram, right? Phase plane or the phase portrait. Now this is stable, that is unstable. So this is what we get there, right? So if you want to solve this, so how do I solve this? So solve the equation dy over dt equals to ry and then y over t minus 1 with y at 0 equals to y0. If you solve it exactly the same steps we will follow, okay? So this is what you will get. The solution will be, follow the same steps. Solution will be is, you get y of t is equals to y0 times t divided by y0 plus t minus y0 and then e to the rt. This is what you will get the solution of this equation, okay? This is what the solution of the equation, okay? So what I want to do next is I want to do draw the y versus t, okay? So I want to draw the y versus t, okay? So first of all, what is f of y? So f of y is y prime, because this is dy over dt equals to y prime. Is same as f of y, right, is equals to r y square over t minus ry, right? How about y double prime? Why do you need this? Because you want to know where the solution curve is concave up and concave down, because you know that for the concave upward and concave downward, you need to find out the second derivative, sign of the second derivative, which is f prime of y is equals to 2ry over t and then minus r, right? Okay, now so look at this. What will happen if the value of y is between 0 and t over 2? Let us write down that if so 0 is less than y is less than t over 2, then what happens to that? So that will be, what will be y over t? Y over t will be less than 1/2, right? This y, if you divide both sides by t, then you will get y over, then y over t is less than 1/2. In that case, 2ry over t is less than 2r times 1/2, right? That will give you less than r. So in this case, then y double prime will be, this will be less than r, and that is minus r. That will be less than 0. That is y of t is concave down. In that case, it will be concave downward. Okay. So how about if y falls here? If y falls between t over 2 and then t. Similarly, if t over 2 is less than y is less than t, then y double prime will be positive. Then y of t is concave up. So from this you can basically decide how would the graph of y equals. So this is t, this is y. Let us say there is somewhere there is t is a one equilibrium and 0 is another equilibrium. We saw that, right? So if you do that, this is y equals to t. What we found is t is unstable, meaning that if you start somewhere here, then it will go away, right? So it will go away like this, it will go away. And this is t/2, t over 2. What we just said is, if y is between 0 and t/2, if it is between 0 and t/2, then in that case yt is concave down, right? So you can see that it is concave downward, right? So what do you get there? You get basically like this, right? So it is going away with that concave down nature there, right? But if your y, the initial y value is between t/2 and t, it is concave up, right? Because see, it is t/2 between t/2 and t, concave up, meaning what? Like this. You see that? Like this. So it is the graph of that. All right. So if the initial population, what we can say here is, if the initial population is above the threshold t, that is above the threshold t, the threshold model predicts that the graph y versus t has a vertical asymptote there. How do you see that? Because you see that if you draw the graph, or basically if you draw the phase portrait, that's what you will see. Okay, if you draw the phase portrait, it will go up and then somewhere there will be a vertical asymptote. Okay, so at certain t equals to t star at certain time. In other words, the population becomes unbounded for the finite time whose value depends on y0, t, and r. So basically what is happening is it is concave up, right? It is concave up. Concave up means it keeps going that way, right? It keeps going that way. So there should be certain time here, t star, so that the population will become unbounded. Okay, in that case, if it is above the threshold parameter. Okay, now if it is below the threshold parameter, it will go to the threshold. But if it is even below the half of the threshold, then it will go to the 0. That's what we see. Okay, guys. So the population. So this is all about the threshold, the critical threshold model. It is basically the logistic growth model with critical threshold. Okay, guys. So in the next one, I will combine the threshold and the logistic growth. We called logistic growth with threshold. All right.